Today we are going to learn about mastering efficient image loading with OpenCV. We'll explore optimal techniques for efficient image loading, impacting performance and resource usage in computer vision applications.
Welcome to this video on mastering efficient image loading with OpenCV. Image loading is a crucial step in any computer vision application. Efficient loading not only impacts the speed of processing but also the overall resource usage, making it an essential skill for developers. In this session, we'll delve into OpenCV's capabilities for handling images, focusing on optimal techniques for various formats, understanding color channels, and optimizing memory usage. By the end, you'll have a strong foundation to improve performance in your image processing tasks. The imread function is a cornerstone in OpenCV when it comes to loading images. It's used to read images from various file types like JPEG, PNG, BMP, and more. The basic syntax is cv2.imread filename, flags, where filename is the path to your image file, and flags determines the way the image is read. By default, it reads the image in color, however, it can also load images in grayscale or with the alpha channel if specified. While imread is quite powerful, users often encounter issues such as incorrect file paths or unsupported file formats. A common fix is to ensure paths are correct and files are accessible. Knowing how to use and troubleshoot imread efficiently is vital for effective image handling in OpenCV. Choosing the right image format can significantly affect loading times and performance. JPEG is widely used due to its balance between quality and file size, but it's a lossy format, meaning some detail is lost during compression. On the other hand, PNG is lossless, providing high-quality images at the cost of larger file sizes and longer load times. BMP is another option, offering uncompressed images, which are very large and slow to load. When working with OpenCV, consider the trade-offs between speed and quality. For applications where speed is critical, such as real-time processing, a compressed format like JPEG might be preferable. For applications requiring high fidelity, PNG might be better suited despite the slower loading times. Images can be read in either grayscale or color, impacting both processing speed and memory usage. Grayscale images are single-channel images, meaning they only contain intensity information, and are smaller in size compared to their color counterparts. RGB images, on the other hand, have 3 channels: red, green, and blue. While color images provide more information, they are larger and require more processing power. For tasks like edge detection or basic pattern recognition, grayscale images are often sufficient and more efficient. However, for tasks involving color differentiation or complex scene understanding, RGB images are necessary. Understanding these differences allows for better decision-making when optimizing your image processing pipeline. Efficient memory usage is critical, especially when handling large datasets. OpenCV offers several flags within the imread function to help manage memory. For instance, reducing the image resolution before loading can significantly cut down on memory usage. Another technique involves using the cv2.imread_reduced_color_x or cv2.imread_reduced_grayscale_x flags, which load images at a reduced size and are useful for applications where full resolution is unnecessary. Balancing memory usage and performance is key. While reducing memory can speed up processing, it might also lead to loss of detail. Understanding how to leverage these settings in OpenCV will enable you to handle images more efficiently, even on resource-constrained systems. Working with large image datasets presents unique challenges, especially in terms of time and resource management. Batch processing is one effective strategy, allowing you to load and process multiple images simultaneously, thus saving time. OpenCV can be combined with libraries like NumPy and multiprocessing in Python to handle batch operations and parallel processing. This approach utilizes multiple cores of the CPU, greatly speeding up the process. File I/O operations can also be optimized by using efficient data structures and libraries such as HDF5 or Dask, which handle large datasets more effectively. These strategies are crucial for maintaining performance and efficiency in projects involving extensive image data. Image resolution plays a crucial role in both the quality and performance of image processing tasks. High-resolution images provide more detail but require more memory and processing power. Conversely, low-resolution images are faster to process but may lack necessary details. OpenCV provides functions such as cv2.resize to adjust image size according to the application's needs. When resizing, maintaining the aspect ratio is important to avoid distortion. This can be achieved by calculating the dimensions manually or using helper functions. Striking a balance between resolution and detail is key to optimizing performance while ensuring the necessary information is retained for accurate analysis. While using the imread function, several common pitfalls can occur. One frequent issue is path-related errors, often due to incorrect file paths or missing files. Double-checking paths and using absolute paths can help avoid these problems. Another issue is unsupported file formats, where imread may not recognize certain image types. In such cases, converting images to a supported format before loading can be a solution. Additionally, corrupted images can cause imread to fail. Implementing error handling in your code, such as try except blocks in Python, can help manage such scenarios gracefully. Debugging tools and logging can also be invaluable for identifying and resolving these issues promptly.
In this practical demonstration, we will set up a batch image loading process using OpenCV in Python. First, we'll import necessary libraries, including OpenCV and multiprocessing. The code will iterate through a directory of images, loading them in batches. We'll measure performance metrics such as load time and memory usage to highlight the efficiency gains. Error handling will be implemented to skip corrupted files and continue processing. This approach is highly applicable in real-world scenarios, such as training machine learning models or processing large-scale image datasets. By the end of this demonstration, you will have a practical understanding of how to implement batch image loading in your projects. In conclusion, mastering efficient image loading with OpenCV is an essential skill for any developer working with computer vision applications. By understanding the nuances of different image formats, optimizing memory usage, and handling large datasets effectively, you can significantly enhance the performance and scalability of your projects. We encourage you to practice these techniques and experiment with different settings to find what works best for your specific needs. For further learning, explore OpenCV's extensive documentation and community resources. Thank you for joining us in this session, and we hope you found it both informative and empowering.